Okay, so today we're going to start talking about the mechanical movement of the modules themselves. How on this single axis tracker, there's a mechanical force required to get those panels to turn throughout the day. So we're interested in finding out what that force is as a demonstration here. First thing we're going to do is to verify that we've got the panels at their sort of starting orientation here. And you can see roughly we're at, say, 62 degrees or so here. That's not terribly important that we be right at 60. This is more a demonstration for us. Right now, the torque tube is resting on bearings around a fixed shaft that's in this trunnion. And those bearings actually bear the weight of everything on top of it, while still allowing the torque tube to twist. So what we're after is to find out what that force is required to twist. Now, a twist or twisting or a torque force can be defined by an arm, sort of a moment arm, so to speak, from that point of rotation, and then a force normal to that. So you can think of this as turning a wrench or something like that. That's where we're applying torque, right? Where there's an arm and then a force normal to that. So we're just going to see for each of these three panels, which individually weigh 40 pounds, not counting the other sort of forces. And we're gonna just simply use a luggage scale here to do this. And what we're interested in, because the force won't be constant throughout this rotation, right? Because sometimes we're working against gravity, and at other times, this is going to be completely counterbalanced. So we're going to start pulling now at a right angle as best we can. And again, this is not terribly important, but we're at 12 pounds here. We're at 14 pounds, 15 pounds, 16 pounds. Right about here is where we're hitting our peak. So let's see what that is. Can you see that? The camera can see. Right around 51 degrees appears to be where we're hitting our maximum, and now the load, so to speak, or the torque is starting to lighten. So the actual number's not terribly important for us at this point, because we're probably not dealing with the final bearings. But this concept of a twisting force, about that moment arm and that force required to turn or twist the tube, is extremely important for the tracker sled. We want to minimize the amount of parasitic load, so to speak, or the amount of energy that we're gathering that we have to use to actually operate the machine. We're going to do a tabletop demonstration next that's going to describe the benefits of being on absolutely flat land, the benefits of being on absolutely level land, and then the challenges for the tracker sled on being on unlevel land. Okay, so we saw outside that we had a pulling force of 16, say 0.2 pounds on the edge of the group of modules, and that is about 3.4 feet, say, from the center of rotation. So that force against that length would equal, when you multiply them together, about 55 foot-pounds of torque. So that's not terribly important, the actual value, but we do realize that what we need is something that's moving extremely slow, but provides tremendous torque. So one analogy is something that's common, is that we have an energy source here, a battery, and almost all these driver drills have two settings, right? One that is meant for driving a screw. We're not looking for tremendous speed, right? RPMs. We want a lot of torque, right? But that same energy could be spent a different way, right? To do drilling that requires lots of RPMs, lots of rotational speed, but relatively little torque, right? So we have cases in everyday life where we have this. It's actually not a whole lot different than the tractor, right? The row crop tractor here. that doesn't go very fast, but has tremendous torque that it can deliver to pull implements, right? Including pulling a full-size tracker sled. In fact, when we have a train, a full-size train of tracker sleds, 250 feet long, actually the tractor will still weigh almost 5,000 pounds more than the entire sled, right, unballasted. So these machines are heavy machinery that can deliver lots of horsepower, not spent on speed, but on torque. So now we're going to talk about some issues on how we get all these panels to twist. So if we have a lot of level land like we have in the Midwest or upper Great Plains, the land is relatively flat. In a lot of cases, it's also, even if there is a slope, it's very, very level. This is courtesy of the glaciers, right, that are responsible for a lot of the geometry, the topography of our land. So largely solar developers right now have been focused on very, very flat land for that reason. Most of the solar trackers that have been developed for very, very flat lands, right? Desert locations and those sorts of things. We want to be able to bring these to farms, and largely a lot of farms in our area are going to be just fine. So when you have that situation, it's just really the drive in the middle, and as we'll see, this is going to be called a slew drive, actually a device that was developed long ago, variations of it, but this slew drive will actually twist that tube throughout the day and move all those panels. Now there can be some difference, maybe up to a degree of difference, and that slew drive just works fine driving a single long tube, right? But we're going to have other situations with the tracker sled that we want to be thinking about so that it can be adapted to many locations. So clearly flat land works, right? Sloped land, right? That is level but sloped is not an issue. Easily, that puts a little bit of bearing, axial load on the bearings, not terrible, maybe 5-10 degrees. Some companies are able to do more than that. But what we're also interested is in cases where we have to transmit the torque, but there might be tracker sleds on slightly different slopes. So just to exaggerate this, we'll do a quick demonstration here. Say I was to put a wood dowel beneath these, and it's barely perceptible. So this is about that point where you're about maybe 1 degree or so out of alignment. And with an extra strong slew motor, this is a slew drive, this is not going to be much of an issue. But if we start going to larger slopes, larger differences in slopes between the tracker sleds, then we're going to have to start thinking about, well, how are we going to deal with this, right? Because we don't want to necessarily limit the land to just those farms that are absolutely level ground. So what would we do in that case? Well, the answer really exists at the back of the row crop tractor, frankly. And we're going to talk about that now, and it's really this double universal joint, or U-joint.